then you get the opposite picture. You all remember this. This is the same picture that we used for the subcritical hop or the subcritical pitchfork. It's just that now you should interpret this as having a circle here, just as you had for the hop bifurcation. But with the hop bifurcation, you also had motion along this circle, and now you don't. Whatever angle you have, that's where you are, and you're perfectly happy. Okay? So we can do more analysis on it. We can write this. You know, I told you before that this was, it just made the arithmetic simpler to do it in complex form. But we can go back to Cartesian form, and we can write it like this. This is just this equation written in its real and imaginary parts. This is exactly equivalent to that. But it's more telling to write it in polar form. We saw this before with another case, I forget which one. Let us write z equals r e to the I theta. If z equals r to the I theta, then z dot is equal to r dot e to the I theta plus r I theta dot e to the I theta, or r dot plus I r theta dot e to the I theta. And that's just what's written in that green expression. And on the right-hand side here, we wrote mu minus the modulus r squared times r e to the I theta. If we were just to write the real and the imaginary parts starting here, we would get these same equations because it would be the same. But let us instead divide through by e to the I theta and now write the real and the imaginary parts. And when we do that, we get r dot equals mu r minus r cubed, and theta dot equals 0. Meaning the r undergoes a pitchfork bifurcation. This is the pitchfork form. And the theta, well, it doesn't move. That's what we said before. It's not as if it goes around and around trying to find its perfect point, the pen. It just goes wherever it is, and theta dot is 0. We can use what we learned about Jacobians and eigenvalues to learn about the stability, to just do the computations that go with this picture. This picture really tells you everything, but we can do the computations that go with it by doing the Jacobian. Let us, for the origin, we have to use the Cartesian coordinates because polar coordinates are not defined at the origin. You can't decide on a theta, right? So let us go back here and let's take the Jacobian in these Cartesian coordinates. We should get the derivative of this with respect to x is going to give us mu minus 3x squared, right? The derivative of x cubed is 3x squared. So that's what we get, mu minus 3x squared. And then the derivative with respect to x, again, we get minus y squared, and that's what we have. We have minus 3x squared minus y squared. The derivative of that expression here with respect to y is minus 2yx, and that's what we have here. And the same for the bottom. Now, as I said, as we said before, it's always good to have practiced with Jacobians. Jacobians are matrices, but they are to be evaluated at a point, usually a fixed point. Okay, so we see this is a matrix, and it's to be evaluated at x and y, as particular values of x and y. We said we have a fixed point at 0. We said that, well, here we have 0. So let us evaluate it there. We get mu, yes. We get 0, yes. We get 0, yes. We get mu. We have a double eigenvalue mu. We looked at that the first time. This, in the first class, we looked at things just like that. When we talked about the Jordan block, this is the thing that's not the Jordan block, right? It has the same eigenvalue, mu, in both directions. So that's the situation. We have either this, if mu is negative, or we have this, if mu is positive. And this, the choice of drawing them in this way, x and y, is completely arbitrary. You know, we could draw them. What we mean is that we're going in, and we're going in at the same rate, no matter what angle we're at. Okay, and that's what that previous picture is supposed to describe here. It's not just x and y, it's everything in between. Okay, so that tells us about the, that tells us that at mu equals 0, which is something that we saw already from the equation, at mu equals 0, we change the 0 solution changes its stability, becomes unstable. You go from this situation to that situation. Okay. Now what about the states on the circle? For here it's going to be more interesting to use polar coordinates, easier, more interesting, and it's going to be possible because once we're on the circle, not at 0, we can define an angle. We can't define the angle at when we're at r equals 0, but elsewhere we can. So let's go here to these equations. Let's take the derivative of this with respect to r. We'll get mu minus 3r squared. The derivative with respect to theta is 0, and everybody else is going to be 0. So we will get mu minus 3r squared, and everybody else is 0. Let us evaluate this. Remember the points, here I don't have an alpha, I took alpha equal 1. The points on the circle are r equals square root of mu. So let me put in mu minus 3 mu. That gives me minus 2 mu. So here these points on the circle have two eigenvalues. One of them is minus 2 mu, and one of them is 0. Right? Everybody remember that the eigenvalues of a diagonal matrix are on the diagonal, and so we see minus 2 mu and 0. These are the eigenvalues. Mu has to be positive, otherwise we couldn't have had this circle. So this eigenvalue is negative, and this is in the radial direction. Remember, the top row is r, the bottom row is theta. So in the radial direction, we have inwards motion. That is the arithmetic that goes along with these arrows, saying we contract radially into that circle. In the other direction, we have 0. And I think we discussed this before. I said that a 0 eigenvalue means I don't care. I'm neither going to expand nor contract. I don't care. And that is indeed so. That is the fact that we haven't drawn any arrows saying, okay, I'm here, fine. I don't care. I'm not going to leave. I'm not going to go anywhere. That's what a 0 eigenvalue means. It means it's not that perturbations grow, nor do they come back. If I'm here and I move to over here, well, okay, I'm just as happy to be here. I have no desire to come back where I was before. All these angles are the same. That's what we saw with the pen. Once the pen is lying down, if I decide, oh, I don't like this direction pen, I'm going to put the pen over here. It doesn't say, oh, wait a minute, I'm in the wrong place and try and come back. It's equally happy at all the places. And that is what that 0 means. It means perturbations neither grow nor decay. Okay, let's not do this, the next thing. Let's see. Yeah, okay, maybe we can do this. Here is, okay, so we saw so far in a situation with rotational symmetry, we saw a new kind of bifurcation, new situation called a circle pitchfork. Now I'm going to show you another situation that combines a circle pitchfork with a regular pitchfork. And these are going to be the equations for it. This equation you already saw, r dot equals mu minus r squared r. That's what you just saw. Before you had theta dot equals 0. We're going to have it instead be zeta. And zeta is going to be some other direction. It's going to be in this perpendicular to the plane that we've been looking at. And the equation for zeta is going to be like pitchfork. They say there's a cubic term and there's a linear term in zeta. It's going to be a little different. Let us see the behavior. I'm not motivating the choice of these equations. I'm just telling you, I'm putting them down, and I'm telling you these equations describe some physical situations. Okay, so let us see what happens as you increase mu. Okay, for mu negative, well, we know we have only one, let's look again for fixed points. For mu negative, we know that we cannot make this 0 except by having r equals 0. If r is 0, we have minus 1 minus zeta squared. All of this is negative. The only way to make this 0 is to have zeta equals 0 as well. So you just have theta dot, everybody's 0. Okay, so that is mu negative. Here we are, a homogeneous solution, just a 0 solution. That's the only one that exists. Now let's let mu be positive. When mu is positive, we know what happens. We just saw it over here. This is what happens when mu is positive. You have a circle's worth of solutions. Okay, mu is positive. And r is equal to square root of mu. R squared is mu. So we have mu minus 1 minus zeta squared. Until mu gets to be 1, okay, this r squared minus 1 is going to act like its own kind of mu. And when r squared is less than 1, meaning when mu is less than 1, then this thing can't be 0, and this thing still has to be 0. Okay, so we have a solution. This is the zeta direction in and out of the plane here, and it's 0. And we just have a circle pitchfork. Now, when mu becomes greater than 1, then this thing here we can get a new fixed point of this equation and this equation by having we can have mu minus 1 be equal to zeta squared when mu is greater than 1. Then mu minus 1 is positive, and so mu minus 1 minus zeta squared can be positive. So we don't need to have zeta equals 0 anymore. We can have zeta be square root of mu minus 1. But then theta dot is not 0 anymore. So what are these equations telling you? For mu negative, we have a single solution which is 0 for everybody. For mu between 0 and 1, we have a circle and no rotation. Zeta is 0. And for mu greater than 1, there still exists that circle, but there exist other solutions which are also circles because you have r, any r, the radius just has to be equal to mu, that is radius of mu. But you have rotation, and zeta can be either positive or negative. So what you have is you have first a point, then you have a circle, and you don't care where you are on the circle. And now, instead, so first this one becomes unstable, and this one is stable. And that you've seen now many, many times. Right? This is the one that's stable. So you have any angle. Now, this becomes unstable. It becomes unstable in a pitchfork sort of way, not circle pitchfork, but ordinary pitchfork, where it becomes unstable and it has instead two guys in front and behind it. Just like when you went to, when you just had going from this to this. Just two guys. So you have a circle here that's unstable, and then you have a circle here and a circle here. This circle has become unstable, and this one is stable, and these are two new circles here that are each stable. But that third direction is zeta, and it's telling you that you turn along those circles. So you have this one where you're not turning, and you have this one where you turn clockwise, and this one where you turn counterclockwise. And that's what this picture is showing here. And this is called a drift pitchfork. And why this word drift? Because you recall, as soon as you form these new circles, zeta is rising from 0. Just as in any pitchfork, it started off, if you just look at zeta here, it was 0, and now it starts off as 0. So it's small when it's first formed, meaning that the speed is slow. And so a word for slow motion is drift. You know, when you think drift, so you have this stationary circle, and right after the bifurcation, you have one in front that is going like this, and one just behind that's doing. And this is an actual situation that we saw in some chemical, in a chemical pattern, where there were two variables. This is plotted, u and v as a function of x. And you had these two waveforms. One of them is u and one of them is v. And you had either motion, you see this square thing here, and then this kind of, right, you have the square, and then you have something that looks like that. So you ended up with the two circles, in this case, were a function of this periodic degree x, the periodic variable x here, and this direction here was symmetry breaking. It was the anti-symmetry in the function. You can see that this one looks symmetric. It's not actually symmetric, but it looks almost symmetric. This one here, you can clearly see the anti-symmetry, the asymmetry. You see that it does this. And there's one that looks like this, and then the other one, the other function, looks like that. And this is true in general. In general, if you have a function, if your solutions are functions of some periodic direction here, x, and if they are reflection symmetric, then they wouldn't know which way to go. If your function looks a little bit, say like this, then that allows it to go. Okay, perhaps it depends on what the situation is, but something that looks like this, you can imagine maybe it travels in this direction. And then in that case, by the same kind of principles we're talking about, there exists another solution, an equivalent solution, that looks like that, and what do you know? It travels like that. A solution that is perfectly symmetric will not go to the right or go to the left. It wouldn't know which way to go. But if it's a little bit different, if it's if it's got some little thingy like that, then it has a direction in which it prefers to go. Okay. So this is a situation in which you successively broke the rotational and then the reflection symmetry. Let's see. We can talk about the difference between. Let's see. I think when is a good time to break. Let's have a break now, and then I'll do something else. And then, as I said, we'll stop early. We're going to stop at 11:45. So let's do a 10-minute break right now. First, can I ask if there are any questions? Okay, so in about 10 minutes, we'll start again.